The next type of probability we're going to discuss is going to be based off of real data. And what I mean by that is theoretical is what should have happened. This next type of probability we call relative frequency. Relative frequency meaning the event has already occurred. Let's go ahead and calculate some things based off of that now. Here's what actually did happen. And in this one, it's basically the same thing. We're going to look at instead of looking at the total number of outcomes, we're going to look at what actually has occurred, how many things have actually occurred versus what we're actually interested in. So, example 4 says, geological records indicate that a river has crested above flood stage just 4 times in the past 2,000 years. What is the relative frequency probability the river will crest above flood stage next year? So this is based off what already has happened. And so we're going to find the probability of an event, the probability of the river crest, and we'll use the letter C there, is equal to how many times did it actually crest? Well, it only has crested 4 times. Out of how many years have we been looking at this? 2,000. So the chances that it crests are 4 out of 2,000, and we can express it as a decimal if we wanted to. And as a decimal, that's equal to 0.002. So again, this is based on what actually has happened and not what should happen. But again, realize that they're pretty much the same exact things. Get the next one. You're interested in only the number of heads when tossing 2 coins. Then the possible events are 0 head, 1 head, and 2 heads. Suppose somebody actually did this. So you repeat a 2-coin toss 100 times, and your results are as follows. Let's calculate the relative frequencies here. So the frequency of each event is 0 heads 22 times, which means you flip tails. You flip all tails when you flip those 2 coins. There's 1 head 51 times, and there's 2 heads 27 times. The relative frequencies are going to be written like this. We flipped it 100 times. So the first one for 0 would be 22 out of 100. Next one would be 51 out of 100. And then the last event would be 27 out of 100. If we compare these two there to the relative frequencies that are theoretical, well, here's what should happen. Well, again, when you flip 2 coins, we've already did this. Let's do it again. You get a head or a tail. If you flip a head the first time, you can get a head or a tail again. If you flip a tail the first time, you can get a head or a tail. And again, this leads us to the events. Head, 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 tail, tail, head, tail, head, tail, tail. And again, if we're only interested in, we'll define a variable x, let x equal the number of heads. Remember, we made that chart on the first example, or on the second example. So we get this chart that looks like this, where your possible number of heads are 0, 1, and 2. And the probability of x, or the probability of getting a head, 0 heads we said was 1 out of 4. 1 head would be 2 out of 4. And then no heads would be 1 out of 4. Well, if we flip a coin 100 times, we'd expect to get, based off of these probabilities, let's change these to decimals. So 1/4 is 0.25. 2/4 is 0.50. And 1/4 again is 0.25. So if we multiply those decimals by 100, we get this. 0 heads, you'd expect to get, or 0 heads, you'd expect to get that 25 times. 1 head, you'd expect to get that 50 times. And 2 heads, you'd expect to get that 25 times as well. And if you compare them to the relative frequencies up here, they're fairly close to these. 25, you're off by 3. Here you're off by 1. And here you're off by 3 again. Here you're off by 2. So notice how that this probably is a fair coin that we're flipping. Now, if it were truly fair, we'd expect to get all of these to be in line with these numbers right here. But why is it not that? Well, that's because when you flip this coin, there's going to be some error based off or some variation because you're actually doing the experiment. So look at the last one. It says your friend claims that he can read minds as an experiment. You play the game of paper, rock, scissors 30 times. You get the following results. Based on these results, do you really believe that your friend is a mind reader? Well, again, this is saying, let's compare this. We need something to compare this to. And we can see that the relative probabilities, the relative frequencies are going to be these right here. The probability of a win is equal to 6 out of 30. The probability of a loss is equal to 13 out of 30. The probability of a tie is equal to 11 out of 30. Compared to what actually happened, or compared to what should happen, the probability of a win should be, we play 30 times, there's a 1/3 chance you're going to win. So 1/3 of 30 is 10. 10 out of 30. Probability of a loss is also 10 out of 30. Probability of a tie is equal to 10 out of 30. If your friend claims to be a mind reader, what would you expect to happen? Well, in 30 games, you'd expect them to win a whole lot of games or either lose a whole lot of games on purpose if they're doing it the other way. So with 6 and 10, that means he's only 4 out of what should have happened. Here, they're only 3 out of what should have happened, and here, they're only 1 out of what should have happened. So could this have occurred by chance? Yes. Did it probably occur by chance? Yes. Is your friend a mind reader? Probably not. The other type of probability that we're going to discuss is what we call subjective probability. And it uses what we call experience or intuition. For instance, when you walk outside and you see gray skies, you don't need somebody to tell you to bring an umbrella because the chances that it rains are probably going to be pretty high. So that's based off of experience of what you've seen before when you see gray skies. So that's what this type of probability is. So we look at example 7. I want to go through all 3 types of probability. Remember, there's 3 types. There's the theoretical, which is what should happen. There's relative frequency, which is what actually happens. And there's now the subjective, which is what you think or what, from experience, what has happened. So decide which type of probability is described in each situation. I'm 100% certain that you'll be happy with this car. Is that something that you can actually prove? And that's how you decide if something is subjective or not. Can you actually prove it? Well, can you actually prove that somebody is 100% certain about something? No, you can't. So this is what we call subjective probability. It's based off of feeling or an intuition. Based on government data, the chance of dying in an automobile accident during a 1-year period is about 1 in 8,000. Well, this is based off of underlying data from something. Because it's based off of data, this is what we call the relative frequency. Something you have data is going to be relative frequency. And then the last one's probably rolling a 7 with a 12-sided die is 1/12. Well, that's what should happen. You roll a 7. To roll a 7, there's a 1 in 12 chance if you have a 12-sided die. So this is what we call the theoretical probability. Now, this is going to lead us to our final thing, the probability, in terms of the rules, what we call the probability of it not occurring. And we give this a special name. It's what we call the complement. So we call it the complement. And the word complement means not. And here's how the not part of something works. Since the probability of a family of 3 children having 1 girl and 2 boys is 0.0375, what is the probability of a family of 3 children not having 1 girl and 2 boys? Well, again, if you go back and look at our tree, we can verify this probability is 0.375, which is 3 out of 8. So this is basically 3 out of 8. And we know that all of the probabilities have to add to 1. And because they have to add to 1, we can use this thing that we call the complement. And we write the complement like this. The complement of the event is the probability of E, C. And the C up here means not. So the probability of not getting this event of 1 girl and 2 boys, let's call that event E. We'll say the probability of E complement. So this is not getting 1 girl and 2 boys. Well, we know the probability of getting 1 girl and 2 boys is 0.375. If I want to find the probability of not getting that, I can take that away from, I know that all the other events have to add to 1. So if I do this, I can do 1 minus 0.375, which this 0.375 represents the probability of 1 girl and 2 boys. What I'm doing now, I'm taking that away from the entire sample space. And when I do that, I get 0.625. So this may be easier to see. Let's look at paper, rock, scissors. Find the theoretical probability of not winning a game of paper, rock, scissors. Let's write out the sample space again. We know the probability of a win is equal to 3/9. The probability of a loss is also equal to 3/9. And the probability of a tie is 3/9. And again, we said that when you add all those up, so when you add 3/9 plus 3/9 plus 3/9, you get a sample of 1, or 9/9. So you get an outcome of 1. Now, if I want to find the probability of not winning, so take this event winning, the probability of not winning can be written like this: winning complement. But what does it mean to not win? We can look at it and see that it means to not win. That means you either lost, or you can, in this case, you can tie. So we can see that this is equal to just 3/9 plus 3/9, which is 6/9. But using the complement now, because we want to be introduced to, the complement says I can take 1 minus the probability of the actual event, which is winning. And here, if I notice, what is that doing? That's saying that, well, these all have to add up to 1 to be the sample space. And because they all have to add up to 1, what I'm going to do now is I'm going to take away what I don't want from that. And I'm interested in not winning, so I don't want the win. So I'm going to take those away from it. So this breaks into 1 minus 3/9, because that's the probability of winning. And again, this is a 1, so we need to make it to a fraction because we're subtracting fractions. So that's 9/9 minus 3/9, which is 6/9. So this is the concept of the complement. The complement says take away from the sample space what you don't want. And we know we take it away by the sample space has to add up to 1 with the probabilities. Take away what you don't want, and it gives you everything else.